we're going to work out this problem. And here we have the 4 things they want us to find. They want us to find the total impedance, the Z sub t. They want us to find the voltage across the 2 ohm resistor, V1, and using the voltage divider rule. And they also want us to find the current I1 right through this R2 using Ohm's law. That same value is going to go through these 2 as well. And so we also want to find the total current source. That's another thing they want us to find. But if you look at this circuit, it looks pretty complicated. And you have right here this strand looped all the way up to the top. But you also have this loop right here. This loop means that the only thing that's connected to here is the resistor and this capacitor, the R1 and X of C2. It also shows that X of L1, X of C1, and R2 are connected individually. But what we should notice here to redraw this circuit to make it more easy to simplify and handle is that this point is at ground. So is this point. This point represents the capacitor here, the resistor here, and the inductor here. So all of these ends go to ground. If we look at these top points, this represents R2, which is connected directly to that inductor through the capacitor, and it's also the top of this R3 that's connected to ground. And then we also have the R1 connected to that capacitor X of C2. So they're all part of the top source. So to make this look easier, put E there, positive, negative. And I'll just go ahead and simplify. Well, I'll redraw this because it's probably going to look much more simpler when I do it that way. As opposed to me using blocks, because we haven't really solved for any of the impedances yet. And this will be a way to do it. Because we'll do the actual drawing on the big board. So I'm doing the resistor and the capacitor here to ground. Then I'm going to do, let's just do the resistor. So the resistor to ground. Let's see, this is R1. This is, well, if I want to put R2 next, I'm going to use this one. So let's put that there, put the capacitor there, and the inductor there. So this is X of L, this is X of C1, this is R2, oh, yeah, C1, this is X of C2. And you could write them the other way. I could have left this other resistor in this strand and put this strand, or this column over here, but that don't need to. They're still going to be done the same way. Because if you look, they're all in parallel. But I still have to do these series combinations first. And it's probably good if I write the values here. 2 ohms. X of C2 is 2 ohms. R2 is 3 ohms. X of C2 is 2 ohms. And X of L is 6 ohms. And we got 60 volts. That angle is 0 degrees. So this is how we solve the circuit. You could put these as blocks. I got some room here, I could do that. Let's make Z sub 1 equal to R1 plus X of C2. And then Z2, that's going to be equal to R2 plus X of L plus X of C1. Why do I have x of c2 written here? Not sure why that's there. That should, oh, x of c2, that's 2. I don't know why I wrote that. It should be just 2 ohms. There we go. X of c1, that's 9 ohms. All right, so now making sure we got everything consistent here. Okay. Also want to put V1 here. Positive, negative there. Our IS is here. ZT is also here at this point. And we also are going to find this current I1 flowing through this branch. So we're gonna find I1 through Z2. And then Z sub 3, well, that's just equal to R3. But before I move it to the big board, I'm gonna redraw this circuit real small down here, but I'm gonna bring these values together so that it's a much smaller circuit. And I'm gonna refrain from putting the values here. Always good to draw a ground first, or establish a ground in any circuit you're actually building. Still didn't get the 2 right, but that's how the circuit ends up. We have three impedances in parallel with each other. The first impedance, Z sub 1, is R1 in series with X of C2. The second impedance, Z sub 2, is R2 in series with C1 in series with X of L. And when we add these together, we'll end up with 3 ohms because the 9 is negative and the 6 is positive, and so we'll have 3 ohms at an angle of negative 90 degrees, which is more of a capacitive load. Well, we're going to move on to the next part for this. All right, so now we're going to work out the algebra of these problems. And our first solution we want to find is the total impedance. And so we can find the total impedance just by doing the product over sum of Z1, Z2, and Z3. So here's Z1, here's Z2, and here's Z3. All right, RE is actually 60 volts. And angle 0 degrees. Let's do Z2 in parallel with Z3. So let's just make that Z4. That's equal to Z2 in parallel with Z3. And that's equal to Z2 times Z3 over Z2 plus Z3. Well, we know that Z2 is up there. We have R2 plus XL plus X of C1. Let's just write out the equations here, and then I'll write out the values of the elements. That way we can just do the algebra pretty quickly. Z sub 5, that's going to be equal to Z1 in parallel with Z sub 4, because whenever we redraw this circuit from doing this simplification right here, we end up with the source in Z1, the grounds, and then we have here Z sub 4. That's in parallel. That's parallel with Z sub 1. Now we could do the same thing here. That's going to be equal to Z1 times Z4 over Z1 plus Z sub 4. Okay. Z sub 4 is Z2 parallel with Z sub 3. So let's just replace this value with this. Oh, and since Z sub 5, we should just Z sub 1 parallel. That's just make that ZT. That's the total impedance. That's actually what we're looking for. So this little two lines represents the same thing above it. So this can be consistent with other variables when you're doing the calculations. This Z sub t is going to be equal to Z1, and that's going to be times Z4, and Z4 is this expression. So Z2, Z3 over Z2 plus Z3, and we're dividing that by Z1 plus Z4. But Z4 is this expression, so Z2, Z3 over Z2 plus Z3. The best way to deal with this is probably just plug in numbers and solve for Z1, Z2, and Z3. Because, or we could, if we really wanted to solve for this, we could find a common denominator here, which would be Z2 plus Z3 on both of these sides. So if we multiply, let's do that. Multiply both sides by that. Let's see what happens here. See if my algebra is as good as it should be. This is a product of that. So Z2 plus Z3 times this over this is the same thing as 1 over 1. Z2 plus 3 divided by Z2 plus 3 is 1. So it's the same expression. We're just going to rewrite this in a different way. So this becomes Z1, Z2, Z3 divided by, we're going to multiply this by both sides. So this over itself, which is 1. This by that. So we'll actually end up with Z1, Z2 plus Z1, Z3 plus Z2, Z3. Because we'll multiply this expression times this and times this. This denominator goes away and we're left with this. But this times this, we get Z1 times Z2 and Z1 times Z3. And then this expression is what's left. This is actually the total expression we need in order to solve for Z sub t. Now, it's probably good to write that here since I got that. All right, here's our first problem, Z sub t. So let's get these values. R1, let's see, R1 is 2 ohms. R2 is 3 ohms. X of L, 6 ohms. We have 2 capacitors. X of C1 is 9. X of C2 is 2. C1. X of C2 equals, what was that? 2 ohms. And then we have R3. I should have put that here. X of L, 6 ohms. R3 is 10 ohms. All right, so we have all the values. We know that Z sub 1 is R1 plus X of C2, and Z sub 2 is equal to R2 plus XL plus X of C1. So let's just plug this in and see how this turns out. These are all products, so it's probably best to have these in phasor notation. R1 is 2 ohms. X of C2 is 2 ohms. This is minus J2. ohms, and that's equal to, and we're also going to do some products here, so it's probably good to have all these in phasors notation right now. All right, clear the screen. 2 squared plus 2 squared. And the square root of that, 2.83. And the angle, negative 45 degrees. All right, and then this one, our R2 is 3 ohms, so we have 3 and X of L, which is 6 plus J6. And then we have X of C1, which is minus J9. That's all ohms. This becomes 3 minus J3 ohms. And I'm pretty sure that the same degrees will be negative 45. The magnitude is going to be 4.24. So Z sub 2 is equal to, I don't want to do that because I like to put boxes around answers. Z sub 2, 4.24. Negative 45 degrees, straight inverse tangent of negative 3 divided by 3, which is the same as 1, yeah, negative 45 degrees. Okay, we got Z1, we got Z2, now all we need is Z3. Well, Z3 is easy because that's just a resistor, R3. Z3 is equal to 10 ohms, which is equal to 10 ohms and equals 0 degrees. So now we can plug all this in. Z1, ZT is equal to Z1, which is 2.83. Ohms at an angle of negative 45 degrees times Z sub 2, which is 4.24 ohms. At an angle of negative 45 degrees. When we add these two together, these angles together become negative 90. But then we have Z sub 3, which is 10 ohms at an angle of 0 degrees. We're going to divide this whole expression by a denominator of something in these square brackets. And I'm going to put these in parentheses so we can see them easier. 2.83 at an angle of negative 45 degrees times Z sub 2, which is 4.24 ohms at an angle of negative 45 degrees. We're going to add that to Z sub 1 again. Times Z sub 3. And add that to Z sub 2 times Z sub 3. Then run out of room. Now, I left the angle off of this one because we don't really need it. It's just magnitude here. We're adding zeros and a point and adding we're having to write that extra point there. Let's see. I'm going to save 2.83 value, the whole value as A, and then the 4.24 value as B. Negative 45 degrees is easy to remember. So A times B times 10 is actually 120 on the dot. And here, ohms times ohms times ohms, ohms squared at an angle of negative 90 degrees. We've got a capacitive value on the top. But it might change because of the denominator. So 2.83, I'll say A times B is 12 ohms. And that's at an angle of negative 90 degrees plus, and I'm going to write that as negative J12 ohms because we're going to add all these values together, so it's better to do it, better to have them in that notation. This is pretty easy, 28.3, and we're going to subtract that, so minus J of 28.3 ohms, multiplying 10 by 2.83, and the negative 45 degrees. Oh, I could write this if it was negative 90. This I can't because these are added together, but this is negative 45 degrees, so I still have to write negative 45 here. I can't just leave it as a negative value. Actually, I can't put negative J. I gotta write minus. Let's just figure that out now. 2.83, which is B, times 10. No, 2.83. Where did that come from? Oh, that's A. A times 10, right. And then that times the cosine of negative 45 degrees is 20. And then that value times the sine of negative 45 degrees is negative 20. So we have plus 20 minus J20. So this is 12. That's negative J90. It's a negative 90, so that makes it negative J. And we're going to plus 20 for the resistance, minus J20 for the reactance for this. And then this one, it becomes 42.4 ohms at an angle of negative 45 degrees. So B times 10 times the cosine of negative 45 is 30, which means we're going to add 30 and subtract 30 because it's negative 45 degrees. So make sure that's right. That value times the sine of negative 45. Yeah. So now that we do this, this here we could just leave the same. And this becomes negative J minus J30 is negative 42, negative J42, but we're going to add 30, so because negative 12. We end up with 20 minus J12. Because these cancel, I'm sorry, this is 30, this is actually going to be 50. 50, that's the X values. This becomes negative 50 J, and this becomes negative 62 J. J62 ohms. Now total impedance is 50 squared plus 62 squared, and 79.64 ohms at an angle of the inverse tangent of negative 62 over 50. It's negative 51.1 degrees. Negative 1 degrees. But that's this here is not Z sub t. Right here, we're gonna take this value divided by this value. This here is 120 ohms cubed at an angle of negative 90 degrees. We're dividing it by, this becomes 50 minus J62 ohms, which this is actually equal to 120 ohms cubed at an angle of, well, actually we have products of 2 ohms here, so this is actually ohms squared here and here. Correction, that's got to be ohms squared.
All right, we're good. So then rewrite this, but this here is going to be a new value, and I already did the math here. 79.6 ohms at an angle of negative 51.1 degrees. We do the math here. We take the 120 divided by that 79.6 and do it right. .51 ohms at an angle of negative 90 minus negative 51 becomes a plus 51.1, negative 38.9 degrees. This is consistent with the answer that's in the back of the book. 1.52 ohms at an angle of negative 38.89 degrees. I'm happy with that. Now that's Z sub T. That's just the total impedance. But we know what the total current flowing through the circuit is now. There's E to T. Here's E. We're going positive to negative to positive from the current flow. As long as there's a ground, there's a path of current. And we're looking for this value of I. Next, well, the second one's find the voltage V1 across the 2 ohm resistor using the voltage divider formula. The 2 ohm resistor is R1. R1 is the voltage across Z1. And even though these are all in parallel and they share the same source voltage, the voltage divider formula only needs to be applied with R1 and X of C2. So V1 is equal to E times the voltage at R1, which is equal to E times R1 divided by Z sub 1. So that's 60 volts at an angle of 0 degrees. Multiply that by R1, which is 2 ohms at an angle of 0 degrees, and divide that by Z sub 1. We have that calculated here to be 2.3 ohms at an angle of negative 45 degrees. This negative 45 degrees becomes a positive on the final solution. This becomes 120 divided by A, which is at 2.83. And we get 42.4 volts at an angle of 45 degrees. Now, check the back of the book for that one. Okay, 42.43 volts at an angle of 45 degrees. That looks good. Now V1. Now part C wants us to find the current I1, and I1 happens to be the current that's flowing through R2, which is Z sub 2. Well, that's easy. All we got to do is just take E divided by Z sub 2, and we have the whole current flowing through both the R2, X of C1, and L, X of L. So that's an easy one. So I1 is equal to E R2 divided by Z sub 2. Oh, I'm sorry. That's using voltage divider formula there first. This is equal to E divided by Z sub 2, which is equal to 60 volts at an angle of 0 degrees divided by Z sub 2 for 4.24 ohms at an angle of negative 45 degrees. Again, this final result will be a positive 45 degrees. And that value becomes 28.3 volts at an angle of 45 degrees. Let's check the back here. Usually I have them written on a dry erase board just so I have quick clarification, but I do look in the back to make sure I got these right. Now, okay, C saying 14.14. What did I do wrong here? E divided by entire gives us the total current. Going through that.
Find the current using. Oh, that's why. I took 120 divided by that value. So I just divide that final answer by 2. 14.14. 14.1. I had 120 instead of 60. So yeah, 14.1 volts is the answer for that. And then the final one, find the current IS. The source current, oh, we could have done that in the beginning. That's E divided by Z sub T. 60 volts at an angle of 0 degrees divided by, what was that? 1.51 ohms at an angle of negative 38.9 degrees. So the total current flowing through the source and 39.7 amps at an angle of 38.9 degrees. Yeah. And I had to look at that one just because most times we have current values that are really, really small. This is a very significant amount of current for this problem. That's how this is solved. This is how this one is solved theoretically.